Hey everyone, welcome to This Explainer. We're putting on our statistical sleuth hats today to investigate some data patterns. Whether you're diving into Grade 8 Algebra I or you just really want to sharpen your data detective skills, you are exactly in the right place. In this explainer, titled Two-Way Frequency Tables and Conditional Patterns, we're going to learn how to organize messy, real-world data, find hidden connections, and most importantly, avoid the traps that raw numbers can set for us. We'll be building tables, calculating conditional percentages, and learning how to compare associations the right way.
Here's our super quick roadmap for today. 1. What is a two-way table? 2. Building the frequency table. 3. Counts versus conditional percentages. 4. Association is not causation. And finally, 5. Recap and transfer question. Let's jump right in.
All right, Section 1. What is a two-way table? Defining our tools.
Okay, so before we start crunching any numbers, we've got to define our notation, right? A two-way table, which, by the way, statisticians sometimes call a contingency table, is basically this brilliant way to organize data for two completely different categorical variables at the exact same time. Think of categorical variables as just descriptive buckets, like your age group, your favorite color, or what we're about to look at, gender and favorite hiking spots. We organize one variable into horizontal rows and the other into vertical columns. And where they cross, boom. That is where we record our data. Oh, and those outside edges, those are our marginal totals, which literally just tally up the rows and columns so we can see the big picture.
Moving right along to Section 2. Building the frequency table. Constructing from scratch. Let's set the scene here. Imagine we're tracking the hiking area preferences of a randomly surveyed group of 100 hikers. Our two categorical variables are gender, so we've got rows for women and men, and hiking preference, which gives us columns for the coastline, near lakes and streams, and on mountain peaks. Plus, we've got our total row and column hanging out on the margins. Right now, it is a totally blank canvas.
Let's drop in the raw counts we actually got from our survey. We know 18 women prefer the coastline, and 16 prefer lakes and streams. We also know 14 men prefer mountain peaks. And let's say our survey told us we have exactly 45 women and 55 men in this study, which gets us to our grand total of 100 hikers. But wait, we have several blank spaces. We've got a bit of a mathematical mystery on our hands.
Which brings us to our first pause check. I actually want you to pause this explainer right now. Grab some scratch paper and use the values we already know to solve for those blank spaces. You know, how many women prefer mountain peaks? How many men prefer the coastline if we know 16 men do? Try to fill in the whole grid. Go ahead, I'll wait.
All right, welcome back. So here is the immediate reasoning to decode the rest of this frequency table. Honestly, it's just a series of mini algebra puzzles. For example, to find the women who prefer mountain peaks, you just take the row total of 45 women and subtract the knowns, so 18 for the coast and 16 for lakes. 45 minus 34 leaves us with 11 women who prefer peaks. And you just do that exact same horizontal subtraction for the men, assuming we also discovered 16 men prefer the coast. After that, you simply add vertically to find the column marginal totals. Simple as that.
And here is our fully worked, age-appropriate example. We can clearly see all 100 hikers are accounted for. We've got 34 total people for the coastline, 41 for lakes and streams, and 25 for mountain peaks. Our rows add up, our columns add up, and everything balances perfectly right there at our grand total of 100 in the bottom right corner. Seriously, excellent detective work.
Okay, Section 3. Counts versus conditional percentages. Avoiding number traps.
Now, I want you to listen closely to the story these raw counts seem to tell. Consider this data. 18 women prefer the coastline, while only 16 men prefer the coastline. At a quick glance, you might just shout, aha, women naturally prefer the coastline way more than men do. I mean, 18 is bigger than 16, right? Case closed.
But hold on a second. If you jump to that conclusion, you are walking straight into a classic statistical trap. We absolutely cannot just compare raw counts when our sample group sizes are totally different. Remember those marginal totals? We surveyed 45 women but 55 men. The playing field isn't level at all. Comparing 18 out of 45 to 16 out of 55 using just the raw numbers is literally like comparing apples to oranges.
So, time for our second pause check. Knowing that those raw counts can be super misleading, how do we level that playing field? Like, how do we calculate the row conditional percentage for women who prefer the coastline? Go ahead and pause the explainer again and see if you can figure out how to turn that raw count into a fair, comparable rate.
Okay, let's break down the immediate reasoning here. To find the row conditional percentage, you first isolate the specific condition, in this case, being a woman. You take the raw count of 18 and you divide it by the total number of women, which is 45. 18 divided by 45 gives you 0.40. Multiply that by 100, and boom, you get 40%. This tells us that conditional on being a woman, there is a 40% rate of preferring the coastline.
By the way, you can absolutely look at this vertically too. If you want to know what percentage of all coastline lovers are women, you'd use a column conditional percentage. You'd take the 18 women and divide by the total number of people who like the coast, which is 34. 18 divided by 34 is roughly 52.9%. Honestly, whether you use row or column percentages depends entirely on which direction you're trying to analyze the association.
And this right here brilliantly illustrates exactly why rates matter so much. When we look at those row conditional percentages, 40% of the women prefer the coastline. But for the men, well, 16 divided by 55 is only about 29%. Comparing 40% to 29% reveals a much stronger and, more importantly, an accurate association. By using rates instead of counts, we correctly identify that a significantly higher proportion of women prefer the coastline compared to the proportion of men.
Which brings us to section 4. Association is not causation. The golden rule.
So we found a mathematical association, right? But there is a foundational rule of statistics that every data sleuth literally must respect. Our source material hits the nail on the head with this rule. A relationship between two variables does not mean that one causes the other to occur. Yes, we found an association between gender and hiking preference, but we must never claim that correlation proves causation. Think about it. Being a woman doesn't biologically cause someone to walk to a beach, and being a man certainly doesn't cause an aversion to sand. There could be a dozen other confounding variables at play: geography, free time, social groups, you name it. We report the association neutrally, but we never, ever declare causation.
Finally, section 5, recap and transfer question. Test your skills.
All right, let's lock these major takeaways into your memory. First up, always define your notation before you start: rows, columns, and marginal totals. Second, remember that two-way contingency tables are explicitly designed for categorical variables. Third, always use conditional percentages, never raw counts, to compare associations when your sample sizes are different. And fourth, say it with me, never claim that correlation proves causation.
Now it's time for your transfer question. We have a brand new set of data straight from our source material regarding athletes, stretching, and injuries. We've got a row for 350 athletes who stretch, with 55 of them getting injured, and we have a row for 450 athletes who do not stretch, with 231 of them getting injured.
Based on this two-way table, here is my final question for you to solve on your own. Does the conditional percentage of injuries for athletes who stretch differ from those who don't? I want you to calculate the row conditional percentages for both groups, compare the rates, and see what kind of association you find. Honestly, you might be totally surprised by the results. But hey, before you use this data to swear off stretching forever, remember our golden rule. Is stretching actually causing the injury rate to change, or is there some hidden, lurking variable we haven't considered yet? Think critically, keep sleuthing, and thanks so much for joining me on this explanator.